Welcome, everyone, to this episode of Manufacturing Talk Radio. I'm Tim Grady. I'm here with my co-host, Lou Weiss, who is also president of All Metals and Forge Group. They do open die forgings and seamless rolled rings for the industrial marketplace. If you're looking for large rings, medium-sized rings, all kinds of custom-shaped forgings, check it out at steelforge.com. Joining us today is Daniel Herrington. Daniel is the CEO of Voxel Innovations. And Daniel, you've got an interesting background in how you got into your own company. Give us some, and by the way, I'm fascinated that you were an IndyCar driver. So give us some background on Daniel.
Sure. So yeah, throughout undergrad and after undergraduate, I was a professional race car driver trying to make a career of it there. So I was racing in Indy Lights, which is a step below IndyCar, and some sports car racing like the 24 Hours of Daytona. That was a very enjoyable period of my life. Very exciting profession I was pursuing there. It became very difficult to raise sponsorship dollars in 2010 during the recession, as you can imagine. That's some of the first things people cut spending on was advertising and motorsport spending. So I had this passion for engineering and technology and manufacturing and ended up going back to graduate school. So sort of left the racing world behind. It still tugs at my heartstrings now and again, but I went to graduate school at Duke University in engineering management, which is sort of like an MBA for engineers. And from there went to work at the Department of Energy at specifically a group called ARPA-E, the Advanced Research Projects Agency for Energy, one of the government long acronyms, mouthfuls. So it was really there where I started to get interested in the role manufacturing plays in enabling some of these innovations, whether it's in energy manufacturing, transportation, you name the industry, manufacturing is often at the core of enabling some of those new technologies. And the piece that was very exciting to me was how new manufacturing technologies could actually help drive new innovations in cleaner energy technology or new airplane engine technology. And so that started to become a real passion of mine. And I left ARPA-E to go, I did some consulting looking at additive manufacturing, metal additive manufacturing, worked for a company called Metam, who is now part of GE Power, that did specialty hole drilling and gas turbine blades, and really was introduced to this electrochemical machining process through those experiences. And this electrochemical machining process is more widely used in Europe and the US than in the US. And I saw a big opportunity here in the US to both educate people on what the technology is and provide that capability and service, but also to develop new technology that helps transform and generates the next generation of electrochemical machining processes.
I remember Metam is in Parsippany, New Jersey.
You got that correct.
All right. Know them well. Good company.
Yes.
Well, you mentioned ECM. You want to explain that for our listeners and audience?
Happy to. Yeah. So electrochemical machining has been around since the 60s, really, but mostly in specialty aerospace applications. Only a handful of companies utilized it, primarily turbine engine manufacturers. And the way it works is you use an electrode that's the inverse shape of the part you're trying to make, very similar to how sinker EDM works. And you move that electrode close to the workpiece. And as you're doing so, you're maintaining a small gap, so it's a non-contact process, and flushing an electrolyte solution, typically a saltwater solution, between your electrode and the workpiece. And while that's happening, you apply a voltage potential and pass current through that small gap. And effectively what you're doing is high-tech corrosion or high-rate corrosion. So you're literally dissolving the material atom by atom using electrochemistry or corrosion at sort of 10,000 times faster than happens naturally. So really the mechanism is similar to electropolishing, we remove material the same way, and it's the opposite of electroplating. So we're in that family of technologies, but we are just going a lot faster than electropolishing does. I mean, literally 1,000 or 10,000 times faster material removal rates in our process. And so that's, that sort of fundamental technique has been around, like I said, since the 60s. But in the last couple decades, there's been some innovations that we're trying to drive as well, including more advanced power supplies. And now you can apply pulses of potential instead of a constant DC waveform. That can enable better accuracy. We can also vibrate our axes up and down pretty rapidly, 10 to 50 or 60 hertz. And that can also help improve the accuracy and repeatability of the process. And new technology on the software side is also making the process easier, more repeatable. Still has a long ways to go and still has some challenges, but these innovations that we're seeing and sort of leveraging what's happening in computer science and simulations and even wastewater filtration are all helping make ECM, sort of reinvent ECM. Often we refer to it as pulsed ECM or precision ECM as sort of the next generation of this technology.
What's the temperature of the electrode?
Yeah, so everything, because it's an aqueous solution, it basically has to happen at below boiling point of the water. But more commonly, we're at 40, 50, 60 degrees Celsius at most in the process. So it's inherently pretty low temperature, which means that it's very low stress. So not only are we not contacting the surface, we're not thermally removing the material like a laser might or EDM might. So that low stress is a real benefit to this process as well.
So what's the kinds of materials that you can use this technology on?
Yeah, so this is like other non-conventional processes. One of its strengths is that as long as it's a metal, basically, it needs to be electrically conductive. We don't care that much about any of its physical or mechanical properties. We just care about the chemistry. But we can machine a single crystal nickel superalloy or hardened tool steel about as fast as we can machine aluminum or copper. So it means that we think about materials a little bit differently. Traditionally, actually, materials that are very difficult for us were things like refractory metals, so molybdenum, niobium, tungsten. Those don't often do well in a standard electrochemical machining process. It's actually an area of funded research on our part by the Department of Defense. We're developing a new method for machining those refractory metals to try and expand our portfolio. But at this point, we've probably worked with 60 different material types: nickel, iron, cobalt based materials, aluminums, coppers, and then some more exotic things like titanium aluminide or high entropy alloys. If it's metal and conductive, we've got a good shot at machining it, and we don't care if it's tough or gummy.
Daniel, what's the real world application? And by the way, one of the things I want you to get into, something you touched on, we were chatting previously about, is that when you're working on something for the DOD or the DOE, you're also, on the left side of your brain or the right side of your brain, trying to figure out how to commercialize it.
Yes. Yeah. I mean, increasingly, actually, the government funded work, they will not fund you unless you have a clear idea of how you're going to turn this into some commercial product. So we spend a lot of time thinking about what companies we can align our research efforts with, so that when the research effort's done, we've got a pathway to make it into a real product. So the applications are kind of varied. We initially focused on aerospace and medical because there's this high concentration of difficult metal alloys, tight tolerances, smooth surface finish requirements, and some of those industries pretty high volumes as well, which is a good fit for us. Our process requires a fair bit of development of the electrode and the process parameters at the front end. So if you asked us to make 1 or 10 parts, it's really not a good fit. But if you want us to make 100 or 1,000 or 1,000,000 parts, our process starts to become much more attractive because we can amortize the cost of that development and the tooling over volumes of parts. But I sort of think of the applications where we are best suited in a couple ways. One, if you have a hard to machine material, it just makes us more competitive relative to other processes. We are not going to compete with a milling operation making a big flat plate. That is not our good competitive area. Or our turning or OD grinding operation, not a good fit for us. Those are sort of planar or cylindrical surfaces. But when you think about parts with lots of feature density on them, think of a microchannel heat exchanger or a turbine disc with a bunch of blades on it. These are repeated features on the same part, and we can leverage a couple of strengths of the process, namely that as the workpiece area gets larger, our process doesn't slow down. We need more current over that larger area, but we can still fundamentally go at the same sinking rate. So this is different than most every other process. It's more akin to a stamping operation in that mindset that, if you make an electrode that's twice as big, or you want us to make, instead of one part in parallel, we're going to make 5 or 10 parts simultaneously. We need more amperage to do it, but we can still move at the same rate. And so you can get much higher throughput with this process. And so whether that's parallel parts or parallel features, we think of them the same way.
Does your equipment have multiple electrode heads so you can do multiple jobs at the same time?
So
Or multiple
sort of. So we don't do different geometries simultaneously, but we will do this multiples of the same part simultaneously.
Got it.
So our tool might have copies of the same thing, and we're doing that in parallel. And that could be, a plate where you've got multiple features on it, and we're doing them all simultaneously, or it could be independent parts that are put in parallel.
Is this a quick process time-wise?
Yeah. So the material removal rate can be quite fast. We're not going to outcompete a hogging operation on a CNC machine, but when you think about removing the last 5 millimeters of material and trying to get final tolerance, where you've got these very small features, thin slots, thin walls, where you would normally have to go slow or use a surfacing routine on a machining operation, we can be a lot faster than those techniques. It does take us more time to figure out the right process parameters on the front end and develop the tooling and manage the electrolyte flow. But once we get that down, in many cases, it is one of the fastest ways to produce a part when it fits within those parameters. Like I said, not hogging material, but creating sort of final features with this process.
So when if a machine shop, for example, is making a part, they've got an order for 500 widgets, but they don't want it. They don't either have the capacity, their equipment can't do close tolerance. So they would then could ship it to you to do the final near net shape dimensions.
That's correct. Yeah, there are really sort of 2 types of customers we often deal with. Some are people where the part is already in production. The design's released, they're making it with some method, and maybe they're looking for an advantage, a way to make it a little bit faster, cheaper, what have you, better service quality. And those applications can be hard to find sometimes, because often when you design a part, you are really designing the manufacturing process at the same time. And so we kind of have to displace another technique. So that can be a good fit when the volumes are high. If you're talking low volumes, it doesn't justify the switching a new process and that sort of thing. And the other type of customers we deal with are often they're OEMs or a larger tier 1 manufacturer earlier in the design phase, where a part's going into production in the next 6 months or 6 years. I mean, literally that sort of time span. And they're trying to figure out what's the best, most efficient way to make this thing. And they might have a little bit of flexibility on the design as well. They might be able to change a feature here or there to better suit our process, either to make our process faster, or in some cases we can enable some feature that they didn't think was possible. Maybe making this wall half the thickness it was originally, and that leads to some performance benefit. And so whenever possible, we love to be involved early in the design phase of these projects so we can help educate people on what the process is, what it can do, what it can't do. That's all part of that design for manufacturability discussion. But we also get a number of customers that they're in production. They just need a better, more efficient way to do it. And we can help them as well. We just, they need sufficient volumes to really justify it.
Daniel, before we forget, how about giving us your website address and an email so people can reach out and get more information directly from you?
Sure. Our website is voxelinnovations.com. That's V as in Victor, OXEL, the word innovations with an S on the end.com. And if you email info@voxelinnovations.com, that comes straight to me. So I'll see all those emails. You can also find it on our website. There's a form you can fill out there as well for that method. And our website has we put a fair bit of time into content on our blog specifically to try and tell people about what our process can do and, as importantly, what it can't do. And in the context of certain materials or applications. So we're really just another tool in the manufacturing toolbox, but it's one that many people are not aware of outside of some niche applications. So, to be a good manufacturing engineer or manufacturing supply house or designer, really, it's helpful to be educated on all the techniques and technologies that are out there. And that's part of our mission, is to help that education process.
So, good, Tim.
Daniel, do you do any webinars out to the manufacturing industry to tell your story?
We haven't yet. It's a good idea. We have, prior to COVID, attended a couple of conferences, or manufacturing conferences in aerospace and medical, and spoken there to try and educate those attendees on what it is we do. But we are actually just recently have been putting more effort into the marketing education side of things. So I'll take that under advisement.
Yeah, it sounds like pretty high tech, very interesting processes. Just one quick question as we kind of wrap up here, Daniel. I, as a consumer, not as a large multinational corporation trying to produce hundreds or thousands or tens of thousands of parts, but I, as a consumer, where am I likely to be impacted by this technology?
Yeah, so you probably will never see it, but when you step on an engine or an airplane and you see those engines hanging off the wings, guaranteed there are parts in there that are made by electrochemical machining today. If it's a GE or Pratt & Whitney engine, there are ECM parts in there. If you have surgery and get a stapled operation or have some surgical tools inserted in sort of orthoscopic surgery, there's a good chance that you might have tools that are made by PECM in that process. So you may not see it or know it directly, but you're probably not that far away from some of these products. We're hoping so that it's way more common in the future that you run across parts that are ECM'd. So we'll see where that goes in the next 5 or 10 years.
Well, we hope you're wildly successful enough so that you can become a team owner of an Indy car, and that way you'll get back into the game.
Yeah.
By the way, I've heard it rumored that race car drivers have a lot of girls that are attracted to the drivers. Is that true?
I think that's a rumor.
Didn't work for you, huh?
Yeah, I met my partner after I left racing, so maybe that's a sign there.
Okay.
That's the Hollywood version.
That's right. At least it wasn't true for me, so maybe I'm too much of an engineering nerd for that to be the case.
Well, Daniel, thank you for being with us. We appreciate you sharing this very high-tech, innovative stuff on Manufacturing Talk Radio.
Great. Thank you guys for your time.
You're quite welcome.
And we want to encourage all of our viewers to go to jacketmediaco.com. You can see that website address over on Lou's screen. And as always, thank you for joining us on this episode of Manufacturing Talk Radio.